Lesson 1 is exponential functions, and in 1.1 we're going to introduce exponential growth and decay. And a lot of real life situations can actually be represented by exponential growth and decay models. So that's how we'll start off. So up at the top, exponential growth. The human population can grow at an exponential rate. For example, if one person has 2 kids and each kid has 2 kids, the family would grow at the following rate. So this first line, that 2 to the 0 power, think of it as like maybe like the 0th generation, that initial person. So anything to the 0 power is 1. So 2 to the 0 power would be 1. And then the next line, 2 to the first power is 2. 2 to the second power, 2 squared is 4. 2 to the third power is 2 times 2 times 2, that's 8. 2 to the fourth power is 4 2's being multiplied together, it's 16. And 2 to the fifth power is 32. So that first person, like that was just one person, and then that one person has 2 kids, and then each of those 2 kids has 2 kids. They have 4 children between all of them, and then if those 4 kids each have 2 kids, they have 8, and so on. You can see the pattern. So if I were to like kind of add up all the people in this family, I would add all of these lines. It wouldn't just necessarily be the 32, it'd be the total of all of them. But by that like 5th generation, there would be like 32 new children. Okay, so we can write a function to kind of represent this situation. So in order to do that, you'll notice that like one thing that's staying pretty consistent or completely consistent throughout all these lines is they're all 2. Like all these powers have a base of 2. So that's going to be a part of our function. And then the thing that's changing is that exponent. So it's going from 0 to 1 to 2 to 3 and so on. So that thing that's changing must be our independent variable x. So 2 to the x power. And then we're just going to finish it off as a function. So we'll write it as f of x is equal to 2 to the x power. And in this case, x would represent like the generation number, or like, you know, if x is 0, it's that very first person, like it's kind of hard to think of it as like the 0th generation, but the starting of the family. That when x is 1, it's that first like set of kids that are born. When x is 2, it's the second set of kids that are born, and so on. So f of x is equal to 2x, and then this is actually graphed to the right. And you can see if we follow the graph, it like shoots way up really quickly. Like it kind of starts off a little slow, but the quicker it starts increasing, it just starts going faster and faster and faster. And you could see that with this trend of numbers over here. Like it started off with just like 1, 2, 4, not growing that quickly, but by the end of it, it was already at 32, and it's going to keep going from there. Okay, so this graph, especially, well, the graph and the values, like this is an example of exponential growth because the output values, you know, the 1, 2, 4, 8, and so on, those numbers are growing. And then if you're looking at a graph, the graph is increasing. It's going up and to the right. It's going towards larger and larger y values. So this is exponential growth. One thing I want to talk about is kind of introduce the idea of asymptotes. We'll talk about it more in these notes, but in order to consider like an asymptote, which remember an asymptote is like an imaginary boundary line of a graph, I want to think about what happens on the graph if we start to go to the left side. So like if instead of like just putting in positive x values, I actually start putting in negative x values. So right here, 2 to the negative first power. So when you have a negative exponent, you actually have to take the reciprocal of the base. In this case, the base is 2. So this would become like 1 over 2 to the first power, or just 1 over 2, since 2 to the first power is just 2. And then for 2 to the negative second, it would become 1 over 2 to the second power, or 1/4. And then 2 to the third power would become 1 over 2 to the third, but 2 to the third was 8. So I'm just going to swap that out for an 8, so 1/8. And then if we just kind of continue that pattern, we don't need to continue to write like 1 over 2 to the fourth. It'd be 1 over 16, since 2 to the fourth was 16. And then 1 over 32, since 2 to the fifth was 32. So the point in this is kind of ask yourself in your head, is there any x value that I can put in right here and end up getting a negative? Like, is it possible? Because the more, like, the smaller my x values were getting, I was getting smaller output values. Like, I eventually went to 1 over 32, but I wasn't getting 0, and I wasn't going to get a negative number because it's always going to be 1 over 2 to the x, and there's no possible value that's going to make that negative or 0. So that means that it's basically impossible to get any negative y values on our graph, or even a y value of 0. So that means that we have an asymptote on our graph. So I'm going to go ahead and just draw it in. For any like kind of more simple exponential growth or even decay function, where it's just like, 2 to the x or 3 to the x or whatever, without kind of more terms within the function, which you'll see later on, this will be the asymptote. So it's at y equals 0. And then you'll see that anytime you have just kind of, we'll call it like a parent function, even though the base can change between 2 and any other number. Anytime you have a base raised to an x with nothing else in your exponential function, you'll have that asymptote at y equals 0. And it's just a boundary line because it's impossible to get a 0 output or a negative output. Okay, so moving down to exponential decay. So what happens to the expression 1/2 to the x as x increases? So we pretty much just kind of did the same thing, because like all of these, we had to take the reciprocal of 2, and the reciprocal of 2 is 1/2. But if we take 1/2 and raise it to the first power, it stays the same, so it's 1/2. If we take 1/2 and square it, you square the numerator and the denominator. So like 1 squared is 1. So that's always going to stay 1. And then 2 squared is 4, so 1/4. 1 to the third power. I'm going to write this a little bit smaller and give myself enough space to write the fractions. So 1/2 squared is 1/4, and then 1/2 to the third power. 1 to the third power is 1, and 2 to the third power is 8. And then 1/2 to the fourth power. 1 to the fourth power is 1, and 2 to the fourth power is 16. 1/2 to the fifth. 1 to the first power is 1. 1 to the fifth power is 1. And then 2 to the fifth power is 32. So you'll notice like now these numbers, if you have a fraction and the denominator is staying the same, but then, if the numerator, the number on top is staying the same, like all these ones are, but the denominators are growing, that number is actually getting smaller. And if you're ever not sure, you want to double check, turn them into a decimal. So like 1/2 is 0.5 versus 1/4 is 0.25, and that's smaller because you have a smaller number in the tens place, and so on. Okay, so as we are like increasing our exponent, we're getting smaller output values, like 1/2 shrinks down to 1/4, shrinks down to 1/8, to 1/16, and to 1/32, and 1/32, and so on. So that means that it's losing value or it's decreasing in value, and the word that we use in terms of exponentials is decay. It's decaying. So when we look at a graph, you can see like this graph is going kind of down and to the right, so it's losing value, it's decreasing, it's decaying. And then I just want to kind of show both graphs in like the image. So just kind of notice that like when you have an exponential growth, it's trending up and to the right, similar to like a positive slope would. And then when you have exponential decay, it's trending down and to the right, similar to like a negative slope would. So it's just to take it back to something linear. Okay, and then you'll notice here too, like no matter what value I put in, it's going to be impossible for me to get like 0 output or a negative, because like let's say I take like 1/2 and I don't know, raise it to the 100th power, like that's still going to become 1/2 to the 100th, which is a tiny fraction of a number, but it's not 0 and it's not negative and it's never going to be. So that means that we have another horizontal asymptote here. So that stays true for even decay as well. The only thing that's going to change the asymptote is if there are kind of like other values added around here, and it'll still exist. It would just be shifted, kind of like a translation. Okay, so this is y equals 0, and then we can move down to the general form. And this is kind of like standard form almost of an exponential function, just kind of the order that we write it in. Okay, so general form of an exponential function. We do need it for like the next example, but we will go more into depth in it into 1.2. So we'll kind of go through what each individual part means. But the formula itself is f of x equals a times b to the x plus k. And again, I'm not going to get into what each kind of letter is representing too much because we'll get into that more in 1.2. We just need it for the next example. For the next example, we need to review a couple properties of exponents. So the first one is the power of a power property. So that says that when you have a power like a to the m raised to another power, you can multiply those exponents together. So it would simplify it to a to the m times n. I'm going to do a quick example with some more numbers in there in case that's helpful. So let's say I have x squared, and then that gets raised to the fourth power, so I have a power raised to another power. In order to simplify, I can multiply those two exponents together, so it'd become x to the 2 times 4, so 8. So when you have a power raised to another power, you can multiply those exponents. You can also use that property in reverse if you need to kind of like unsimplify. Okay, so this property actually goes with example 1a, and the second property we're going to use for example 1b, so I'm going to wait till we're kind of on b to review that one. So example 1, rewrite each equation as a function in general form, which is f of x equals a times b to the x plus k, and the first example is y minus 6 equals 2 raised to 3x over 5. So in like kind of the general form, a main part of it is that we want the like b to the x part, a base raised to the x power, to be kind of like isolated. And I'll get like into more about what that means in a second. But one big thing is that we just have that x. There's not ever going to be a number in front of x for that general form. And I mean like in terms of the exponent. And in the problem itself, we have a 3x there. So that 3x is a problem. We need it to just be an x. So that's what we'll take care of first. So I'm just going to leave the y minus 6. And then I'm even going to just leave the 5 in the denominator. But the 2 to the 3x, we're actually going to use the power of power property in reverse. So I'm going to take, let's see. I'm starting off with a product in my exponent, and I want to separate that product into a power raised to another power. So instead of 2 to the 3x, I'm going to rewrite it as 2 to the third raised to the x. If this was just like simple, like a general like exponent property problem, we would be kind of doing this backwards. But since I want to separate that x and have it as my only exponent, this is what I have to do. I have to separate the product of 3 and x into a power to a power. Okay, and then now I can go ahead and I can simplify 2 to the third, and that's why the x would always stay on the outside of the parentheses, and the 2 and the 3 would stay inside, so that we can go ahead and simplify that 2 to the third power. So it'd be y minus 6 equals 2 to the third power is 8, and then that 8 is being raised to the x, I don't need parentheses anymore, over 5. And then when I was saying that we need to like kind of isolate the base or like the b to the x, that means that we have to get the part that's being raised to the x kind of completely by itself. So I have to figure out a way to not really like get rid of the 5, but to separate it out, and it's going to get separated out as a. So I know that a is being multiplied by the b to the x, but and like this 5 is being divided, but dividing something by 5 is the same thing as multiplying by a fifth. So I can separate out that like 5 that's in the denominator and change it into multiplying by a fifth. And then that's being multiplied by that 8x. And then I have y minus 6. And then now I just have to get like the y by itself and swap it out for an f of x. So if I want to get rid of that minus 6, I'm going to add 6 to both sides, and that's going to become this k over here. So I'm just going to add it to the end since there's nothing else for me to add it to, like no like terms. So once I do that, it'd be y equals 1/5 times 8 to the x power and then plus 6. So that 1/5 was the 5 that was in the denominator initially. The 8 to the x, we got that from like the 2 to the 3x, and then the plus 6, that was like the minus 6 that was on the other side of the equation. And then now I'm just going to go ahead and erase the y and switch it out for an f of x. So altogether, f of x equals 1/5 times 8 to the x power plus 6. Okay, so for b, for this one, we do need that second property. So this is the product of a power property, which is when you have two bases that are the same that are being multiplied together, you get to add their exponents. So in this little kind of like formula, we have a times a, they each have an exponent, so we can condense it down into one power by adding their exponents. So a to the m times a to the n simplifies to a to the m plus n. So in like a different example, let's say we have x squared times x to the 5th. They both have the same base, they're both x's, so I can condense that down into one power by adding the exponents, so it becomes x to the 7th. Okay, so b is y plus 7 equals 4 to the x plus 2. And then again, we're starting off with kind of a similar problem as the first one, where as my exponent, I need it to just be an x. I can't have that plus 2 there. So since that has like the sum of two exponents versus the first problem had like the product, since this one has the sum, that's why we have to use this property, because it involves adding the exponents. Okay, so same thing here, we kind of need to go backwards. I'm starting off with x plus 2, the sum, kind of like m plus n. So I need to separate it into two different pieces, like this is here. So if I were to rewrite that, since 4 is the base, when I separate it, 4 is going to be the base of both, and they're going to be multiplied together. And then each of the original exponents, so you'll notice like m and n, those are going to become the powers over the two separate bases. So one of the 4's would become an x, and one of the 4's would have, or not become an x, but one of the 4's would have an exponent of x, and one of the 4's would have an exponent of 2. So same thing here, we kind of like did it backwards. Instead of condensing these two together by adding the exponents, we separated the exponents that were added into the product of two powers. Okay, and then I'm going to bring down the y plus 7, and then I would kind of challenge you, if you can, pause the video here and see if you like can get to the correct answer. If you feel like you need a little bit more example, you can keep playing. Keep playing the video. Sorry. Anyways, okay, so I'm going to go ahead and simplify this 4 squared because we can. So y plus 7 equals 4 to the x power times 4 squared is 16. And this like kind of looks like it's okay in the order that it's in now, but since that 16 is being multiplied by the 4 to the x, so the 4 to the x, let me go back through and kind of code this. So 4 to the x, that's this part, the b to the x. And the number that's being multiplied by it is actually supposed to be in front. So I'm going to go ahead and move that 16 to the front. So y plus 7 equals 16 times 4 to the x, and now it's in the correct order. That's something that when I was going through the notes, I didn't even notice the first time, so be careful, they may kind of try to trick you there. And then now I need to get that constant added to the end, that's going to be this 7. So I just got to subtract over that 7, and then it's going to just tack on at the end. So it'll be y equals, the 7 minus 7 cancels out, so I'm going to write it off to the side again so it's a little bit bigger, but y equals, the 7 minus 7 cancels out right here, and then I have the 16 times 4 to the x power, and then minus 7. So that 16 is a, that 4 is b, and then the negative 7 is k. And then I'm just going to swap out the y for f of x, and then we'll be done. Okay, so f of x equals 16 times 4 to the x power plus 7, or sorry, minus 7, excuse me. And then last thing before we move on is just, yeah, kind of, like I said, the number that's being multiplied by the b to the x, it needs to be out in front. So if you ever have something that's multiplied after, you just need to swap it around. I feel like that's kind of the easiest way to throw in like a little curveball with these problems, so you may see it again. Okay, so example 2, find the asymptote, domain, range, and initial value, and end behavior of the following graph. So asymptote, you'll notice that when we talked about asymptote on the parent function, it was like at y equals 0. That's clearly not the case here, because that crosses through the like graph itself. Okay, so there's always going to be a horizontal asymptote. It's always going to be like kind of what the like graph is trending towards, but it can move depending on what the graph is. So if you notice, like the tail end of the graph right here is trending towards this line. So that's going to be our asymptote. A horizontal asymptote is always y equals, and then it's whatever number where it crosses the y-axis. So this is crossing the y-axis at -4. So it's y equals -4. And then domain is how far is the graph extending left to right. So you could see it's definitely going left forever, and it's definitely going right forever. And that's going to make it all real numbers. So one way of shortening all real numbers is like that r with a double L. The reason that exponentials have a domain of all real numbers is because, I'm just going to use one of the examples we did before, like 2 to the x. There's no limitation on what I can put in for x and get a real number out. I can put in any number, no matter how big or how small, and I'll still get a real number as opposed to like an imaginary number. The range, though, there's definitely a cutoff for the range because there's that asymptote. We have to be above this line. So above that line is y is equal to -4. Above it would have to be y is greater than. If the graph was below it, it would have to be y is less than. And it can't be equal to -4 since there's an asymptote there. It's like in a boundary line, so you can't actually have a point on there. The next part, initial value, that's just another word for a y-intercept. So where does it cross the y-axis? Crosses the y-axis at -3. And then for end behavior, so as x approaches -infinity, that's the left side of the graph. The left side of the graph is approaching the asymptote. So that means that f of x is approaching -4 because that's what our asymptote is. It just depends on, it could change depending on the problem. And then the second line, as x approaches infinity, so x values are getting larger, that's to the right. The right side of our graph shoots upward, so that means that f of x approaches infinity since it's going upward forever. 1.2 is analyzing more rules of exponential functions, so we're going to go through that general form a little bit more in depth. So it's f of x equals a times b to the x plus k. So this is like if you don't have a graph, you're just given the function itself. So if that's the case and you need to find the initial value, you do so by adding a plus k. So a plus k gives you the initial value. B, the base of the exponential, is the growth factor, so whatever is being raised to the x power, and the growth factor is broken down this way. So for growth, it's when a is positive and b is greater than 1. I would say most of the examples you'll see that a will be positive. For decay, if a is positive and b is between 0 and 1. So growth happens when b is greater than 1, any number greater than 1. Decay happens when b is between 0 and 1, like 1/2 or like 0.3. Any number that is between 0 and 1 that gets raised to an exponent is actually going to shrink the higher the exponent goes. And then the last thing is that k tells us what the horizontal asymptote is. So k is the horizontal asymptote, and it'll be the line y equals k. I've noticed in some of the problems they do just kind of ask for the number, so depending on what kind of answers are given to you, just be careful with that. I will try to warn you if you need to like fully type in your answer as like y equals k, because sometimes it is a little bit picky. Okay, so example 1, identify initial value, growth factor, horizontal asymptote, domain, and range from that function f of x equals 1/5 times 8 to the x power plus 6. So this is the example that this is the answer that we found from one of the previous examples. Now we just can find all these different parts from it. So initial value, I'm just going to shorten to IV. And the initial value is supposed to be, it says a plus k. So I'm going to backtrack a little bit, bump this down so we can identify, okay, what is a, b, and k? So A is that constant that's multiplied out in front, so it would be 1/5, or sorry, coefficient. And then B is the base of the exponential, so B would be 8, and then K is just went like naturally in like quadratic order, but K is that constant added to the end, so it's that +6. Okay, so IV, that initial value, is going to be A plus K, so it's going to be 1/5 plus 6, so I'm just going to leave it as 6 and 1/5. If you want to change it to an improper, that's okay. Would be like 31/5 or like 6.2. Okay, and then so we found initial value, and then the growth factor, we'll find that next. It says growth factor is B. So whatever B is, that's going to be our growth factor. So growth factor, I'm going to shorten that to GF, is B, and that's 8. And just leave a note for yourself that means it is growth. It's not decay. So we got growth factor. Next is the horizontal asymptote. So horizontal asymptote, I'm going to shorten to HA. That is going to be Y equals K. So it's Y equals K, which K was 6. So our actual horizontal asymptote would be Y equals 6. We found that value as the constant at the end. And then for domain and range, so for domain of any exponential, like literally anyone at all, is always all real numbers. So we can shorten that to like the R with the double line, because I can put any value in for X and I will get a real number out. Nothing will create an imaginary number there. And then for range, it's dependent on the like where the horizontal asymptote is. So it'll always kind of correspond with this. So it'll be Y, and then it'll be in relation to 6. And then as long as A is positive, like this one is here, that means there's no sort of like funky reflection that flips it upside down. So it would be Y is greater than 6. So if we kind of sketch like a little parent function, it looks something like this, like a very like simple one. This one, yes, there would be some kind of like things that move the graph around, but since there's no negatives, it's not gonna like flip the graph upside down. That would be the only thing that would change the like range from being above the asymptote to below the asymptote and require us to change that symbol to a less than. Okay, so I think we got everything, domain and range, so we can move down to 1.3. (1.3) is exponential functions in context, so trying to identify as much information from these functions in a real life situation. So example 1, Mary made herself some hot chocolate. The function that represents the temperature in degrees Fahrenheit of the hot chocolate is f of t equals 116 times 0.931 to the t plus 68, where t represents the time that passes in minutes. What information can you get about the temperature of Mary's hot chocolate from the function? So I'm just going to rewrite the function down here just so we can like kind of pick out what each value is. So f of t is equal to 116 times 0.931 to the t plus 68. Okay, so we know that a is that number that gets multiplied out in front of b to the x. In this case, it's b to the t as our input value. And then that number that's being raised to the variable, that's our base b. That tells us if it's growth or decay. And then that number that's added kind of at the end, that's going to be our horizontal asymptote, which is k. Okay, so I'm just going to kind of go through almost in the same order as we did up here, where it was just kind of the function itself. So first we'll find the initial value. I'm going to shorten that again to IV. So the initial value is A plus K, which is 116 plus 68. So 116 plus 68 is 184 degrees. So that means that the temperature of the hot chocolate starts off at 184 degrees. And then the growth factor is B, which is 0.931. So that means it is decaying. I'm actually going to change that into a percent just to make a little bit more sense out of the context. So that means that if we were to change a decimal to a percent, you move the decimal place twice to the right. So that means that each minute the temperature decreases by 93.1%. So each minute there's a decrease in the temperature by 93.1%. And then if we were to graph this, the horizontal asymptote, it's y equals k, which in this problem k is 68, so it'd be y equals 68. But we just want to think about what that means in the context of this problem. So that's like our lower boundary line. So that's the lowest that the temperature can get would be 68 degrees. And this is like if we just let it sit out for like an hour or more. So this is the lowest possible temp. And the reason that that's the lowest possible temp is because it must be the room temperature. So if we just let the hot chocolate sit out like the entire day, that's the lowest it can get because that would be the temperature of the room. It couldn't get any lower than that. So the initial temperature of the hot chocolate is A plus K. It's 116 plus 68, so 184 degrees. The temperature is decreasing by 93.1% each minute. And then the room temperature is 68 degrees because that's our horizontal asymptote. It's our lowest. It's kind of like our lower limit. Okay, so example 2, doctors are testing a new medication. The graph represents the rate at which the amount of the drug decreases in the bloodstream after it's been taken. What do the initial value and horizontal asymptote represent in this situation? So for the initial value, when we're looking at a graph, we're looking at the y-intercept. So that's something that you would want to get comfortable recognizing from a problem. If you see initial value, be like, okay, y-intercept, I can find that. So where does the graph cross or start on the y-axis? It's at 300. So the initial value is 300. And if we look at like what the y-axis is labeled as, it's the amount of drug in the bloodstream. So there must be 300 milligrams in the bloodstream at the start of the test. So once they try out that new medication, at the very beginning, there's 300 milligrams in the bloodstream. And then it also asks, what does the horizontal asymptote represent? You can see that, the line is kind of approaching 0, y equals 0. So our horizontal asymptote is going to be y equals 0, and that's because as time continues to go by, as hours go by, the amount of drug in the bloodstream is going to approach 0. So we can say the amount in the bloodstream approaches 0. Okay, so biggest thing from this example is recognizing that when you see initial value for a graph, that means y-intercept. And then the horizontal asymptote, you can see it's kind of like the line that the graph is trending towards. And because it's at 0, that means that that's kind of what the amount of drugs in the bloodstream would be going towards as time goes by. And that makes sense because it's not going to stay in your system forever.